Okay, the next reaction I want to talk about is elimination addition. So it's a little bit different from nucleophilic aromatic substitution, and we're going to see why in just a minute. So if we do this reaction under normal conditions where we have sodium hydroxide, like we saw before, we had it at 70 degrees C. With just the chlorine on a ring, we don't have that nitro group on the ring, we get no reaction. But if we do this at higher temperature and stronger conditions, we actually can substitute that chlorine with hydroxide. Okay, and this reaction works even better when we use a stronger nucleophile like the NH2 in the presence of liquid ammonia. Okay, so NH2 is a very good nucleophile. It's also a very good base, and that's going to be kind of a key to what's happening here. So if we use a starting material like toluene, and we have parachlorotoluene, then in the presence of this soda amide and liquid ammonia, then what we observed was we can get the para product, the para amino product, or the meta amino product in this case. Okay, so where did this meta amino come from? That's a good question. So scientists were interested in this, and they actually used what's called a carbon-14 label. So they put a radioactive carbon in the substrate, and they found that the chlorine was substituted at the carbon bearing the label and at the adjacent carbon at the ortho position. So the mechanism was determined to be that the soda amide, the NH2 minus, can pull off a hydrogen, and in doing so, it forms what's called a benzyne intermediate. So we've got actually a triple bond on that ring. Now, it's not really a true triple bond because we're not going to see benzene in a true sp hybridized situation where it's linear. And so what we get is a really bad overlap with this benzyne intermediate. So it's more like a diradical than it is an sp hybridized bond. Okay, and so it's very reactive, and this NH2 can actually add in to that system, and actually it adds into the pi system there that is not part of the aromatic system. It's adding into that pi system that's perpendicular to the aromatic ring. And when it does that, this lone pair is formed that can actually pull a hydrogen off of ammonia and restore our NH2 minus. Okay, and so then we can get that happen. We can get that to happen at the carbon that was bearing the leaving group and at the adjacent carbon. Okay, so if our lone pair ends up at the adjacent carbon, then that's where we're going to pull off a hydrogen. If the lone pair ends up at the carbon that was originally bearing the leaving group, then that's where we're going to pull off the hydrogen. So the amine group can add in at the carbon that was bearing the leaving group previously, or at that adjacent carbon. Okay, and that was actually verified by using a Diels-Alder. So this intermediate was validated by using a Diels-Alder reaction, where the benzyne intermediate was trapped by using furan as our diene. Okay, and we got this product. Okay, so scientists verified that benzyne intermediate by using a Diels-Alder reaction. So we are certain that that is actually the intermediate that's found in that. So if we want to identify the correct mechanism for aromatic substitution, we need to know whether the reagents are electrophilic or nucleophilic. So we saw that most of our reactions in this chapter were EAS, or electrophilic aromatic substitution. If we have a nitro group, ortho or para to the leaving group, we can get the nucleophilic aromatic substitution. If we don't have that nitro group and leaving group, then we can, when we just have the leaving group being substituted, then we get elimination addition. And those are the reactions for this chapter.